Veľká vďaka a teraz prichádza veľkolepá vízia, teda prichádza pán Vladimír Bužek a bude hovoriť o veľkolepej vízii a umení kvanta, lebo budúcnosť informácií je vraj kvantová. Nech sa páči, máte slovo.
Good morning, everybody. Out of respect to our non-Slovak speaking guests and colleagues, I'll present my talk in English. So during this session, we had a number of very important and very sophisticated issues discussed. So therefore, I think it's time to relax. And in my presentation, I would like to entertain you. I'd like to unleash your fantasy and to join me on a trip to the world of quantum. There are some who might think that we all live in a yellow submarine, though it's not quite true. The truth is that we all live in quantum universe. The universe as it was born in the Big Bang 13.8 million years ago, roughly, it's governed by the laws of quantum physics. It started from big quantum fluctuation. Inflation period is really nothing else than a very sophisticated quantum process. So until today, we live in the world that is purely quantum, even though seemingly it's something classical. Like, this desk is solid. Why it is solid? Because it's a consequence of Pauli exclusion principle. If not for that quantum principle, this desk will not be solid. So classicality is an emergent phenomenon. Everything is rooted in the realm of quantum. As Einstein said, classical reality is merely an illusion, albeit a very persistent one. I put classicality, it's my insertion there. So in order to specify what we are talking about when we talk quantum, I give you 3 minutes crash course on quantum physics. I hope you will enjoy it. So there are 3 pillars of quantum. It's quantum superposition principle, quantum measurements, and quantum correlations. If you understand these 3 principles, you understand everything. So what is a quantum superposition? In this audience, you all know what is a bit. It's your logical unit, 0 or 1. That's it. So this is a classical bit, 0 or 1. It's one or other. However, in quantum physics, we have a qubit, quantum bit. And the quantum bit can be a superposition of both 0 and 1 simultaneously. In fact, to present a state of a quantum bit, qubit, you need an infinite string of bits to express the state of a single qubit. So, quantum superposition, you know everything about it now. Quantum measurements, a bit more complex issue. Outcome of a measurement performed on a quantum system can only be predicted statistically. Quantum theory is a statistical theory. That is, we are using probabilities. Quantum world, at a level of classical information or description, is totally random. It's probabilistic. By performing a measurement on a single qubit, we obtain just 1 bit, either 1 or 0. Depends on the type of measurements you can perform. It can be something else, green or red, but only 1 bit of information. That's it. So, what's happening is that when you perform a measurement on a quantum system, on a qubit, it collapses. It rapidly, dramatically changes its state to the state of the measurement apparatus. That is, there's a information gain versus disturbance. You gain some information from quantum world while you disturb that quantum world by performing a measurement. And as a friend of mine, Chris Fuchs, said, properties that were determined by quantum measurement did not exist before the measurement were performed. Just imagine what that means. Before you perform a measurement, the system doesn't have a property. So you, by observation, by measurement, you create a reality, whatever reality means. Now, we are coming to the 3rd pillar, and it is quantum entanglement, quantum correlations. Everybody in this audience knows what are correlations. 2 things can be perfectly correlated. You know that if you do something here, some other event happens here. You know that perfectly. So out of the set of possibilities, 0, 1 here, you can have 0, 1 here. You pick up 0, 0 is here. You pick up 1, 1 is here. That's perfectly well understood what is a classical correlation. However, in quantum domain, in quantum physics, very strange phenomenon exists. Quantum entanglement, quantum correlations. Imagine two particles, two quantum particles. They are essentially apart across the universe, or at least across the galaxy. So there is no possible signaling. There is no possible communication between the two particles, though they were prepared in a very specific state called entangled state. Interestingly enough, before you perform a measurement on one of the particles, that particle has no property, no specific property. Now you perform a measurement on this particle. It collapses, let's say 0, 1. Let's say state 1. Instantly, at that specific moment, when you make this particle to be in state 1, that other particle across the galaxy is in the state 1. Amazing. If you by chance measure 0, that other particle will be 0 at that instant moment. So this is quantum entanglement. Einstein essentially called that a spooky action and distance. He really was puzzled. He was so seriously puzzled, and he thought that quantum mechanics is fundamentally wrong. Today we know that it's really a fact that quantum mechanics is not a locally realistic theory. That is extremely strange theory that is really contradictory to what we have learned in schools and in the classical world. So I hope that in this 3-minute crash course on quantum physics, you understood, at least you understand the basics of quantum mechanics. And if you think so, then you are totally wrong. As our friend Richard Feynman said, if you think you understand quantum mechanics, you don't understand quantum mechanics. Richard Feynman got a Nobel Prize for quantum field theory. So, now I'd want to unleash your imagination. Just imagine. Tell me, where can we find in the universe most structured, most complex matter existing? Where in the universe that might be? Is it somewhere at the origin of Big Bang? Some black holes? No, the answer is here, in our skulls. In our skulls, we have the most complex and structured matter in the universe as we know it today. So this is the picture of that piece of matter. Now, few facts. The average human brain has about 100 billion neurons. Each neuron might be connected up to 10,000 other neurons and passing signals to each other via as many as 1,000 trillion synaptic connections. Big numbers we are talking. So equivalent, some estimate are saying that it corresponds to a computer with a 1 trillion bit per second processor. The human brain capacity is estimated to be up to 1,000 terabytes. Today, we do not have exact understanding how physical structure of our brain relates to its functionality. But this is the research in neuroscience that is really undergoing extremely interesting research. Now, recently, Jack Gallant from the UC Berkeley reported in Nature paper the following. They made an experiment. They put an observer, a human, a person, a set of sensors on their heads. Right? Some sensors. It was essentially fMRI, that is the magnetic resonance imaging function. That person observed a movie, was watching a movie. Researchers, out of signals from the measurement, were able to recover the image of the movie. Can you imagine? Researchers are now able to to really peek into your brain. They can see, out of following the signal from your brain, they can decode what your brain sees out there. It's pretty amazing. So, and here's the challenge, here's the vision, here's an imagination. Can human mind be downloaded onto a computer? Oh, you you say, oh, that's silly. I mean, how this can happen. First, there's this big philosophical divide, mind and body problem. Nobody exactly knows what mind is. But nevertheless, can we download information content of our brains on a computer? You would be surprised. There are private investors who are investing money exactly into this project, into such a task. Now, what would be needed for that? We know that we would need a better sensor, better measurements. How you essentially be able to monitor signals that our brain is sort of emitting out there, whatever that means. You would need a better memory, higher capacity. I told you that it's estimated 1,000, whatever, terabytes of memory. You would need better processors. You have to really very fastly process the information. And obviously, better security, because you do not want anybody to mess with your mind. Okay, so these are the challenges. So the solution might be quantum computers. Here's the Richard Feynman, who in like 30 plus years ago said, he was the first one who realized that essentially quantum physics opens completely new potential, new possibilities for really processing information. And he thought that quantum physics would allow us to construct quantum computer that will allow us to simulate physics. But today we have an understanding that essentially we can go further, as in my sort of fantasy, I told you, maybe we can do something more. But the quantum computers have the capacity. Processor, it's a very fast processor for the quantum parallelism, because everything can be in a superposition. It's really very, very fast. It has a big memory because the Hilbert space for those registers are exponentially large. So it has a security. As Bill Phillips, the Nobel laureate for '97 in physics, said, quantum information technology is a radical departure in information technology, more fundamentally different from current technology than the digital computer is from the abacus. Please remember that. We are living in an amazing era. So therefore, I really think, I honestly believe that yes, we can download the information content of our brain onto a computer, and probably we will be able to run a mind, your mind, whatever, on a computer. What is needed? Much, much better devices. And what are much, much better devices? They are quantum devices. They are quantum sensors, quantum memories, quantum processors, and this is quantum security. And all this is reality. It's not these devices, as Dr. Kalber will talk just after my talk, these are the devices that are within the reach of our hands. Now, I wonder whether you know who these two gentlemen are. But anyway, the one to the left is Pauli, Wolfgang Pauli, the one who invented the exclusion principle. Gentleman to the right is Niels Bohr, both Nobel Prizes, obviously. And Niels Bohr said, we are all agreed that your theory is crazy. Yes, it is. The question that divides us is whether it is crazy enough to have a chance to being correct. So that's really the question. Now, is it crazy enough? Erwin Schrödinger, Nobel Prize for quantum physics, wrote in 1952, it would be impossible to manipulate individual quantum systems. It's totally impossible. It would be like to raise an ichthyosauria, that is the fish, the dinosaur fish, in zoo. He thought it's absolutely, absolutely impossible. That's forbidden in quantum physics. Now, half a century later, Nobel Prize in physics, exactly for manipulation of individual quantum systems. Yes, we can manipulate. We can manipulate individual photons. We can manipulate individual atoms, trapped ions, whatever. We can do that. We can beat decoherence and other stuff. So it's possible now what was impossible. So what was totally crazy, it was really so crazy half a century ago, now it's reality. Now, if you think that downloading mind, the content of your brain on a computer is a really crazy idea, so let me offer you another. Do you have some time?
Yes.
Okay, thank you. So let me consider something else. Quantum artificial general intelligence. We humans are sort of funny things. So, but maybe there is something much, much better we can invent. And that much, much better might be a generalized artificial intelligence. That is, the intelligence that is really, that performs search algorithms and can learn, that is quantum learning and quantum learning algorithms, much better than us. I mean, that really can pass the threshold of the big data mining. I mean, this is something that really might be the future of all the processing. And is it a future? No, it's a present day research. I mean, if you go to NASA, if you go to Google, if you go to other places, yes, indeed, they do use quantum processes produced by D-Wave. And we can argue to which extent these processes are quantum. There's definitely, I mean, there's a technical discussion. But there is Okay, so this device here is something like a quantum processor. This is a quantum processor, quantum information processor, and these guys are using sort of strings of those devices in order to study generalized quantum artificial intelligence. Now, Hartmut Neven from Google says, in 2 years' time, we can expect from Google a breakthrough in this direction. I mean, we all know that artificial general intelligence is really progressing so fast. Like last year, nobody would be even thinking that computer can beat Go game. Now, I mean, can be so successful in Go game. Now we have it. So the progress is very large, and I'm going to stop soon. The quantum processors, there are a lot of quantum processors. Trapped ions, photons, superconducting qubits. You have Bose-Einstein condensation chips. So there are many, many candidates. Obviously, you can have a candidate like this one, and probably, now, last few slides. Because you are not only, I mean, you are managers, many of you, so I'm certain that you read The Art of War of Sun Tzu, and the first line there is, Sun Tzu said, the art of quantum is the most important art for the state. Okay, the quantum is war in that specific quote, but essentially I think that it's really true. The art of quantum is the most important art for the state. And this is the reason why European Commission, very visionary, essentially announced the quantum flagship. In May, Amsterdam, 2016, the EU Commissioner for Digital Economy and Society, Günther Oettinger, announced that Europe will invest 1 billion euros into quantum technologies, quantum information technologies. And here what we have here is sensing and metrology, sensors. We have simulations, we have computation, we have communication, everything quantum. Okay. Begin at the beginning, the king said gravely, and go until you come to the end. Then stop. I'm stopping. Thank you for your attention.